So you should be live. So I'm giving me an error. YouTube connection there. Okay, let's go find out what's going on.
All right, thank you.
Double check your.
Yep. Oh,
Whoop. Not sure what.
freaking expensive equipment there. Good yourself? Don't mind me on my third cup of coffee here. I'm just going to introduce myself and then you'll introduce yourself.
Can you close the doors? Or no?
Yeah. Close them.
I can close them.
Guess it's 1:30. Let's start, I guess.
Yeah,
Yay.
let's get it going.
How y'all doing today? Good. Awesome. My name is Margarita Rivera. I work for I'm a soil health planner here, well not here, but in Tremont, with the Northern Utah Conservation Service and partner with the NRCS. And I'm here to introduce today our speaker for the day, McKinley Smoot. His bio, I'm going to read him really quick. McKinley was raised on a cattle ranch at the foothills of the Uinta Mountains in Utah. McKinley grew up helping his father implement holistic management on family land. McKinley is partner of 3 Spring Land and Livestock and owner of Living Soils Laboratories. McKinley is an accredited professional with Savory Institute and also a certified lab tech with the Soil Food Web School, and he is becoming a consultant with Soil Food Web School as well. So let me go ahead and introduce him to him. If you guys have any questions, just wait until the end, right?
No.
Oh, throughout?
Yeah, go throughout.
Yeah, let's go throughout.
Have this be more of a conversation.
Sure. All right, here he is.
Is there a camera that I'd need to be in front of, or is this more of an audio-visual thing?
There you go. Yep, you're right there.
Okay, great. So, yeah, I'm McKinley Smoot. Hello. Please, throughout this whole thing, if you have a question or something's unclear, just go right ahead and just shout it out, yell at me, wave your hand at me so I get your attention. So let me just kind of tell you about myself a little bit. I got to click it. Okay. Oh, no, I don't. So my gracious introduction, I'm from Camas, Utah. I grew up on a cattle ranch, about 700 acres on the Provo River, very, very fortunate. And basically the last 5 years I've been really diving into agriculture a lot more deeply. We recently constructed a greenhouse, a geothermal greenhouse. It's about 1,500 square feet, so we have quite a bit of experience in high tunnels. We can grow 12 months of the year if we have lights. And as you can see, this is kind of an interesting before and after picture. This is when we just first started. We backfilled all our soil back in and used, I'm going to take this out, some cover crop to kind of get our system going. And this was just last year. And what we're doing there is kind of a little bit of a polyculture. It's not kind of your typical row production of vegetables. And then I also, this has volume when I touch it, right? Okay. So it's kind of a lot. This is my mother taking this video. That guy right there, this is the ranch that I grew up on. That guy Sherms, he's really the reason that I am doing what I've been doing. He was a holistic resource manager. He got trained by Alan Savory back in 1991 or 92, and that was the year I was born. And this particular year, last year was really bad rain. We lost irrigation on June 16th where we're at, and we're the first priority water, that we're the first people to take water out of the Provo River. And, but, you know, our ground was pretty impressive. So yeah, we'll talk about that. So this is in August, so which is pretty, for where we're at, we didn't get much snow at all. Looks pretty good. We run about 100 head cattle up there. That contraption right there is called a shade haven. It's basically mobile shade. We do holistically planned grazing, and that's one way to introduce really the herd effect in a pretty significant way. And also, you can gain about 85 pounds per year more on a calf if they're shaded. So that's kind of the thing we've been doing. And then I'm also a partner with Three Springs Land and Livestock. They will be doing my business partner Mitch, who's sitting right over there, will be doing a really good presentation. If you have any interest about kind of stacked enterprises, we've been doing beef and chickens last year, and we're looking to expand. And it's everybody here has some pretty serious connection to the land. It's really, once you get that in your blood, it's pretty hard to let that go. The question is how do you make it profitable and make it sustainable? So the other thing that I am is that we've been doing is that we've recently just created a soil laboratory. We do biological assessments using shadow microscopy, and everything we've been talking about has to do with the soil. And without really knowing what's going on in the soil, on basically a community function, it's very difficult to get what you want because it's very simple.
What kind of microscopy?
Shadow microscopy. So what we do is we take soil, the soil that you have, and whatever's functioning in there basically is determining the nutrient mineral cycling of your soil. And so we do assessments for people, help them figure out how to improve that, and usually once you get everything in place, things start functioning much better. And as before, Jimmy kind of talked about is, you see a lot of pictures of the Dust Bowl, right? And you'd think that only happened then. That's still happening in large parts of Oklahoma, northern Texas, southern parts of Kansas, Nebraska. And civilization, it's totally built on soil. The Roman Empire, obviously no civilization falls just because your agriculture collapses, other than maybe the Mayans. But it usually is a serious contributor of things falling apart. Usually, if things are hard on the farm in your family relationships start deteriorating, and if that happens across a nation, usually things get pretty rough. The one I find the most fascinating is the Fertile Crescent, the Sumerian and the Mesopotamian Empire, where, that's where wheat was cultivated. That's where the birth of agriculture is said to have happened. And right there's a lot of instability. That's, the United States has spent the last 20-some years there trying to do whatever we were doing there. And things don't get better. Things just continue to get more extreme. And so in my opinion, I feel like a lot of the strife and political problems and socioeconomic and religious problems that people tend to experience in life comes from insecurity. And usually real security comes from agricultural prosperity. And the soil is totally dependent on that. So a lot of there's a little bit of discussion about what's actually soil. As we're all learning, it's a lot more than just sand, silts, and clays, and clay colloids. The clay colloids and clays are absolutely pivotal to have, but these organisms right here, the aerobic organisms, actually determine the viability of soils. And this is a picture this is kind of an illustration, actually. So it's hard to describe this, because usually a lot of people say if you don't have clays, you can't grow anything. In my opinion, that's not true. This would be, let's imagine you have a silt particle or a sand particle. In that sand particle, there's enormous amounts of nutrients inside of that. The problem is that they're inaccessible to plants. There's a type of soil test, it's called a geological assay, which only, I think Midwestern Labs is the only person who performs that in the United States right now. And they extract all the elements by destroying the actual particle. And they find that there's plenty of nutrients for any kind of plant. Now the problem is plants need soluble nutrients. And how do things become soluble? And that's really the question we need to be asking ourselves. So this is a couple of tables. There was a study done in 2003. A fellow named Sparks, he went across the world and took geological assays from, I think, 300 different locations, many different locations, and did a geological assay. And this scale right here is basically saying this is the amount of micronutrients and macronutrients that are available in all soils, period. Not just in really healthy soils, but in, the sands of the Sahara, the bentonite clay fields that are in, where are those? I think it's part of Iowa and Wisconsin. There's some really high clay soils where people say, this is impossible. This is not something that's you can grow things in. You go out to the West Desert, you say, I can't grow things here. There's a reason for that. We're going to talk about that more. So what we do as people who need to grow things in bad soils is we add it to it, right? So we have all of our inorganic fertilizers, all our synthesized elements in order for us to get what we need. So on the left-hand column in this table, here on the left, this is what agronomists recommend you need for plants, more or less. There's obviously ranges. Now, what the funny thing is, in old-growth forests and in rainforests are actually some of the most depleted soils on the planet. Because often we think it would be because there's so much life, right? Now, the problem is there's so much rain in these areas that they leach out almost all of their nutrients every year. But there's so much biology there that that's actually not a problem. Most of the nutrition is in the first 3 inches of soil there. Now, this is an old growth forest. That was, they put a table of, this is the Pacific Northwest, of what major nutrients are available now, this is much less than what people think we need, right? We need a lot more nutrients than what this old growth forest table would say. And the reason is for that is it's biology. Biology basically goes in, they find these crystalline structures, what's the sand, silt, or clay, they mine it, they excrete enzymes, and those enzymes eradicate the structure. They find, hey, I need nitrogen. Usually bacteria or fungi don't need nitrogen, but they say, my plant needs nitrogen, my plant needs phosphorus, micronutrients, magnesium, iron, zinc, whatever it is. They find it for them and get it for them. This is a cool photo. This was taken this year. This is on a beach in Costa Rica. This is right on the ocean. And this photograph right over here is just behind this photo. And most people think you can't grow things in sand. Nature typically, this begs to differ. This grass right here is incredibly thick, especially on the right-hand side. And that is due to the fact that the plant and the soil are feeding each other the whole time. And so, a lot of people say, hey, I want loamy soil. You do want loamy soil to have a better water holding capacity, but water itself is determined by whether biology is present or not. We're going to talk more about that. Anybody have questions? Please? Yeah, okay.
But what you are saying there is not only pure 100% sand, because it has also silt and clay. What the grass you are growing there now?
It may have had a little bit of clay, but it's mostly sand.
Yeah, but the fine particles, right?
Right.
It's there. That's why those grasses are...
Well, and the grass itself is introducing organic matter, so that there's this constant feeding of the system. Because if it's pure clay, it's the same thing. It's really hard to grow anything. If it's pure sand, but if the biology is present, you can have growth, you can have life present.
It helps both physical and the chemical.
Absolutely.
Right?
Absolutely.
Silt and the sand, more on the physical side, clay on the chemical side. So both work together. That's how it works.
Totally. And you may find clay that's deeper down, maybe.
Yeah.
Absolutely.
You might have one there.
No, for sure. The clay always has more higher cation exchange capacity, and they may seek those out for sure. But pick it up, it's mostly sand if you pick up the dirt. I mean, obviously, if you did an assessment of that, it may be highly dominated sands, but there may be some silts and clays.
80% sand, and then there's silt, and then clay, maybe 5%.
Sure, of course. So this is soil food web. A lot of people have seen this before. And the cycle and nutrient cycle is totally determined by photosynthesis, right? So grasses use CO2. They also use sunlight to then create carbohydrates, amino acids, protein chains, and simple sugars. And those simple sugars feed both bacteria and the fungi. And the fungi and the bacteria are, that rhizosphere that people see, that's typically that sheath of soil that's around that root. That's typically populated by bacteria and fungi. Now that begins to change, assuming protozoa, the higher trophic, the third trophic level organisms are present. And so the protozoa and the nematodes eat bacteria and fungi on pretty high levels. And we're going to get into why that's important, why these things eat each other, why there's sometimes genocides underneath the soil and things are just constantly in a mutual eating society. So we're going to go into each one of these organisms because there's quite a bit of interest, at least I've found. And so what we do is we take an active sample from your soil. We then assess the actual biomass by weight of this is the same microscope that we use, it's a Modig B310E, and we get your report saying exactly what your mineral cycle is doing, whether it actually exists or not. So this is an electron microscope of image of bacteria, of compost. This is very, very active compost. You can see it, we've talked about the bacteria using glues and different kinds of things, sorry, not things, they're not just things, they're enzymes in order to glom on to their food sources, because if they're kind of this free-floating situation, they would begin, they wouldn't be able to feed as well. And so bacteria everywhere. In a complete ecosystem, they're not only underneath the soil, they cover the actual surfaces of plants, and the plants feed those bacteria by feeding them carbon exudates actually on their surfaces. And those bacteria and fungi also are actually very, very important in order for the health of the plant to deter things like pests. So I had a laser pointer, but it's not with me right now. But you can see here on the edge, those are fungal hyphae. And the hyphae, so the little bacteria create small aggregates, and the fungi wrap around those and they create macro aggregates, which then allow for water infiltration and air infiltration. Thanks, Bard. Yeah. Perfect. Thank you. Cool. Yeah. Thank you. So right here, this would be the fungi. These large circles are spores. These spores will germinate in the right conditions, and these fungal hyphae, in order to they create things either like mushrooms, or if they're ascomycetes, they'll create these sacs even underneath the soil, and they'll open up and emit these spores. The spores then germinate and create more fungal hyphae, and the system goes on and on. Now, one of the issues we have is through tillage and a lot of any kind of significant disturbance, whether it be pesticide, herbicide, or tillage, or overgrazing, will greatly damage these organisms. And these organisms, if anybody's interested in carbon sequestration, you will, these guys are the key. Most of the organisms in the soil, bacteria have a 5-to-1 carbon ratio. Bacteria do, and then fungi have a 20-to-1, and then the other higher trophic organisms have 30-to-1. The ratio would be the carbon to nitrogen ratio. So for every nitrogen atom there's 5 carbons. And if you look at a carbon chain of some kind of organism, they're incredibly complex. Now, the thing is, that actually changes with the fungi over time. The fungi, as time goes on, as they mature, they actually keep getting carbon from the plant, and they're very, very concerned about keeping their bodies intact. So as time goes on, they keep layering carbon, so right here is the edges. And as time goes on, as these age, the carbon keeps getting layered into these fungal hyphae. And so as they age, the more and more carbon gets put into these systems. We'll go over kind of what these are. So this right here looks very different from the rest of these, either spores or these fungal hyphae. This is called an omycete. Omycetes are typically disease-causing fungus, so molds, things you don't want. The potato blight in the Irish potato famine was caused by an omycete. That's a functional class. And usually when you start seeing, so that's an omycete. This right here, it's hard to say, but it's likely an ascomycete or a basidiomycete. And the way you can tell by looking at that is because of these septa. These septa are basically creating redundancy in order for these fungi to be more resilient. And then right here, these are fungal spores that are germinating. I'm thinking that these are probably a little bit disease-causing, typically a spore like that, or disease-causing fungi. And these two right here are spores as well. And this right here, the darker they are and the larger they are, the more likely they are to be beneficial organisms. So a lot of people, for us, we're very concerned often about having the right chemical elements in our soils, whether it be magnesium or calcium, and so we add things that our soil needs or seems to be depleted of. And one of the issues is, if you're irrigating or you have a lot of water, you get a large rain event, a lot of that will leach out over time. Again, that happens in the rainforest every year. And so what happens is the fungal hyphae, they act as a net for that. And over time, as they age, they'll form something called oxalate crystals. And these oxalate crystals can be available forms of whatever micronutrient your plant is, as long as they're present. So the problem with tillage is that these are most likely the things to be most devastated in any kind of tillage is your fungi. And so the fungi are an absolutely pivotal part of keeping that in place. So a lot of people have spoken about arbiscular mycorrhizal fungi. There's really two very important, there's three really, but right here this is called a arbiscular mycorrhizal fungi or an endomycorrhizal fungi. Endo means inside, and so fungi actually will infect roots. When you say infect, most people think that's not a great thing. But in this particular case, it's very important they have a mutual symbiosis. So through their ability, so what they do is they go into the root. They can go in fairly deep, about halfway through, and then they act as another, I don't know what it would be. They're searching for, roots are searching for nutrients. And sometimes roots can just find through diffusion, or there's a couple other processes that the root can get the nutrients that they need. But the arbiscular mycorrhizal fungi themselves communicate with the plant. They often will root themselves into other plants and seek out not only macronutrients, which are nitrogen, phosphorus, and potassium, but which are what the plant mostly needs, really for very robust plant health. The plant needs micronutrients, and that would be magnesium, zinc, iron, molybdenum, manganese, all kinds of different things. And these mycorrhizal fungi hyphal strands can go and find that for them. And what's interesting about the fungi, in my opinion, the most interesting thing is that they will manipulate the pH every millimeter depending on what things are needing, because some fungal hyphae can emit different enzymes in order to find and source different micronutrients. So when you start getting into, the highest and best form, actually, I'm going to skip over that for just 1 second. We're going to go into the higher trophic organisms. So when we talk about protozoa, there's really three classes, and those would be amoeba, flagellates, and ciliates. And there's two different types of amoeba. These are known as testate amoeba, and these are called naked amoeba. And testate amoeba are fascinating to me. They're almost like hermit crabs. They create their own tests, which you can kind of imagine being shells, and they will eat 10,000 bacteria a day. And the same thing with a naked amoeba. Naked amoeba seem to be more present on the surfaces of plants rather than in the soil themselves. They do show up in the soil. They're very common. Like in the big oak trees of California, it's very, very common to find these on oak leaves. These are flagellates. Very, very beautiful creatures in my opinion. This one looks like a star. It's called a stellate flagellate. Flagellates use flagella in order to propel themselves through a solution. Soil is a subaquatic environment, and without these flagella, they couldn't move through there. And usually They eat around 10,000 bacteria a day as well. This is called a ciliate. A ciliate, the way it moves itself, these are the race cars of the soil food web. In a soil solution, they zip right through. They'll go all the way from one field of view to the other in less than a second, which is very, very, very fast for a soil organism. And these typically start showing up when your soils are turning anaerobic, or they've been anaerobic and turning aerobic. And what those are called, it's called a facultative organism. Facultative organisms can survive potentially on the border of a certain condition. But these do eat a lot of bacteria, but you don't want to see a lot of those because otherwise you're likely dealing with a situation that's turning anaerobic. And that either means too much water, compaction, just a lack of oxygen. These are nematodes. Most farmers want to hear nothing about nematodes. If they hear they have them, it's most of the time a problem because most of the nematodes that farmers deal with are very resistant to tillage and they're very resistant to a lot of chemical pesticides. The ones we're talking about are called parasitic root-feeding nematodes. These nematodes use this spear, if you can see that, has a spear with a nodule on the end of it. And they shove that spear into a root and suck out all the vital nutrients that that plant needs. There is an argument that these feeding nematodes can be okay in a certain context, like they would feed on roots that could be pruned off. But typically they start showing up in masses. And when they do that, you start losing most of your crops, and crops begin to fail pretty quickly. Now, these organisms right here, these are also nematodes. However, this top one right here is called a bacterial feeding nematode. Those are absolutely pivotal. Most of our soils are bacterial dominated, and it takes a long time for them to become fungal dominated, which we'll go into why that's important. And then you have things, you have nematodes called fungal feeding nematodes. Those are the final, kind of the final step. You start seeing those in your soil, you're probably pretty high up on the regenerative scale at that point because they suck the cytoplasm out of hyphal strands and then excrete NH4 ammonium. Now, so this right here is a fungi. You can see the hyphal strand. And they actually create these loops in order to attract these fungal feeding nematodes, and they trap them and begin to drill holes in them and then suck out the innards of nematodes. So this is the kind of creativity and insanity that actually goes on in the soil. But those are actually very, very important to have. These fungal predators will feed on root-feeding nematodes as well. And the way to get rid of root-feeding nematodes in a way that's holistic, in my opinion, would be to introduce the predator. There are predatory nematodes that are about double to triple the size of a typical nematode, whether it be bacterial, fungal feeding, and they have this massive tooth right here. And once they get their mouth on it, you can't get yourself out. And I've observed only one predatory feeding nematode in my life, and they're much larger and they're somewhat intimidating. Does anybody know what this is? Anybody have any idea? It's a water bear, that's right. So tardigrade, or water bear, very, very important microarthropod. They're some of the most resilient beings on the planet. They do go dormant fairly easy, though. They only come out in the right types of situations. But there are billions of microarthropods that they're very important. Typically, they'll begin to show up in a more fungal-dominated system. But they are made up of whether insects, crustaceans. They're very, very fascinating creatures. But this is the favorite of most people, the water bear. You can send those to space. They will go dormant, bring them back, and they will reappear. So this is very, very important, the nitrogen cycle. As we all know, most of our atmosphere is made out of nitrogen gas. And the way that our plants, the question is, how do plants actively get nitrogen without the assistance of human beings? Without the addition of compost or addition of manures or how does the old growth forest do it? How do these environments that are incredibly resilient do this? So so you have nitrogen-fixing plants, and those are using bacteria like rhizobium that create the infection sites for roots, that create the nodules on legumes. And then you have free-floating bacteria that are in soil solutions that fix nitrogen out of the air, like Azotobacter and Azospirillum. And then the next step, but the problem is plants that get that are very unlikely to want to give up their nitrogen. They've worked really hard. They're working with these organisms in order for them to get that nitrogen in the first place. They're not just going to be like, hey, plant, you have some nitrogen too, or my neighbor. So what typically happens is that plant uses that nitrogen for it to build in its body, and then that plant dies or gets grazed or something happens to it, and then it gets taken down by the decomposers, being bacteria and fungi. Now, what's very, very critical here is that if you have a fungal-dominated system, your soil starts getting just slightly acidic, and when you have because of the enzymes that they release, they're constantly chomping on soil particles and leaving humic acids, and that starts beginning to become a little bit more acidic. So the fungi or the bacteria then get predated upon by protozoa, nematodes, and microarthropods. Now, if you do have that fungal-dominated system, that what they excrete is ammonium. And if it's that fungal-dominated system, it will stay ammonium, which is immediately available for plants. And now the problem is if you have a slightly bacterial-dominated system is it will turn back into NO3 or nitrate, which isn't necessarily a bad thing, but it supports different types of plants that are a little bit more weedy. Or even things like brassica or cold kale crops like that. They seem to be just fine in a bacterial-dominated system. And then there's certain bacteria that nitrify the actual nitrogen that these creatures are excreting. These creatures are eating and excreting. And then that also is available for plants, and then also goes to decomposers. And then if your system starts turning anaerobic, whether it be compaction or whatever else, it makes oxygen less available, it goes back into the atmosphere as either nitrous oxide or, So as we've spoken about this a lot, but really the whole water cycle, it boggles my mind that the top 5 inches or 6 inches of soil basically has a very significant thing to role in the whole ecosystem, whether it be the water cycle or the mineral cycle, energy flow through the system. Without these organisms, every cell in our body has been regenerated by our gut, which is basically this whole system. So, and this image right here, and again, the plants and the soil are really the same thing. You can't remove the two from each other. With a plow pan, typically you're going to find a pretty shallow layer of compaction. You can deal with that by either decompacting it yourself, but the issue with that, every time you run a plow or a deep chisel, the layer that's just beneath that plow is typically going to get compacted. So over time, sometimes we need to go deeper and deeper and deeper in order to make our soil more aerated, and that begins to make that plow pan even deeper. So this is what it looks like over time as soil starts breaking through these plow pan layers and the biology starts chomping on this. This model there isn't, if anybody's ever dug in the ground, they find kind of a boulder that hasn't been disturbed. You might find some modeling, and that's typically from fungi that have been chomping on that boulder. When we were building that greenhouse, actually, we hauled off, I think, where we live, we have glacial till about 2.5 feet underneath the soil, and it's just rocks. And we found that 4 or 5 feet underneath, you would see this modeling on rocks, like actual boulders, and that was from fungi that had been chomping on that for millennia. And eventually, over time, that bacteria and that fungi will eat through that, and the plants are the ones that make that possible. because the plants feed the bacteria, and the bacteria and fungi feed the plant. So this is really fascinating. Does anybody have any idea why plants, when you first disturb an area and you don't do anything to it, you don't plant anything into it, why do weeds come up? Does anybody have any idea why? Yeah. Seeds are in the soil, but do you think there's other kinds of seeds as well, like grasses or?
Yeah, things with the season.
Yeah, it could be. Anybody else? Sunlight? A couple of factors. So, when you till the soil, you expose them to all these organisms to enormous amounts of oxygen. And the problem is that the larger organisms, being the higher trophic, the protozoa, the nematodes, and the microarthropods and fungi are all gone. They've most likely been killed. And what happens is the nitrogen, certain kind of nitrogen shows up when there's a lot of bacteria. And that's either NO2 or NO3. And typically it's a low oxygen environment, but weeds don't store a lot of energy in their roots. They're very, very intense about, I need to get my seed out and I need to be done. And they like that type of nitrogen. So a bacterial-dominated soil is going to have a different type of nitrogen than compared to, say, a deciduous tree environment. So as your fungal to bacterial ratio goes up, which is determined either by soil management practices or lack of disturbance or because of disturbance, a number of factors that way, it's slowly going to go up. So weeds typically enjoy a low fungal to bacterial ratio because the type of nitrogen that's there, which is NO3, nitrate. And as it starts going up, you have a fungal bacterial ratio of, for every bacteria, you have 0.3 fungi. Brassicas seem to like that. That would be, broccoli, kale, cauliflower, and the early grasses and mustards. And then it keeps going up. You have the mid-grasses and vegetables. So vegetable farmers want to be right here. Just slightly bacterial and not overly bacterial. So that would be your, tomatoes, lettuces, your fruiting plants essentially. And perennial grasses and row crops like to be equal fungal to bacterial ratio. As you keep going up, the woodier the plant becomes, the more fungi it likes, whether that be the mycorrhizal fungi, saprophytic fungi, which like to eat dead things. And then occasionally you will get with the deciduous trees, they like it even more. And then the old growth forests, whether it be rainforest or conifer, you have 100 to 1 fungi to bacteria to 501 to bacteria, depending on the situation. So so this was kind of a revelation to me because in our neck of the woods, we see a lot of development, and then sometimes the development stops and they disturb all the soil. And so why do the weeds come up? Well, yeah, there's a huge seed bed there, right? But there's also a seed bed of, that used to be, a field of Timothy grass, or it used to be a field of a perennial grassland. Why all of a sudden there's a thistle and all these other things? It's because the biological profile has changed dramatically. So depending on the situation that you want to have on your ranch or your farm, what you feed your soil determines what ends up growing. So this is, oh yeah, sure. Mm-hmm.
Fungal bacteria, primarily bacteria dominated in that situation. So how can we deal with that?
That's a great question. First, it's going to depend on your context, right? For your situation? What would be your management goals? What would you like to grow? Uh huh. Yeah.
And low pHs, high pH water that's continually being poured onto it. My chances of changing my pH are minimal.
Right. I'll be honest with you. When you have the high salinity water, it's a real challenge. There are ways to handle it. You can use certain inputs. What some people do, I wouldn't recommend it just because of the expense, but they do use humic acid, and they put humic acid into the fertigation system. Yeah, that actually helps a lot. What that does is it complexes the substrate. It binds with the humic acid, turns into something else. The problem is that gets expensive. Really, the way, there's a couple of ways. First, you want to make sure that your soil has air. Fungi don't live in a compact, but you can add it. And everybody has waste on their ranch or farm, and if you can learn how to use high quality compost that's been aged properly, that has the right amount of fungi food, and you apply that either directly or using an extract or put it in your fertigation system, that seems to be somewhat beneficial. This is me and my father where we were making compost this winter. It was like 16 degrees outside. And compost kind of gets a bad name, and it's often due to the fact that
Sides? Or do we want to go a little more?
that's pretty. It got hot. You go to the municipality, they say they're composting things a lot, and usually they're anaerobic compost. They want to get rid of as much material as they can. So buying that and putting that out,
Now let's take the
you're
sides.
getting some material. It might have some nice aeration, but it doesn't have the actual component you have in it. But the best way is to create your own compost, which there's a real art to that. It's not just putting some stuff in there and letting it, rot. That will be pretty gross. It is hard. It is absolutely difficult. And that's why I talk about doing more of the extracts than actually spreading it itself. You can get that pretty far.
The sides? Or do we want to go a little more? You need just a little bit.
So it depends on your management. The soil either adding anything with biology is going to be 100% determined upon management. If for whatever reason you have to till, you're kind of starting over. And every time, in my head, every time I till, I'm eliminating my soil food web, and I'm probably eliminating about 1% of organic matter in my soils. So it's a hard question. These are kind of transitioning to regenerative agriculture, if you've been in a kind of a more traditional sense, is really a challenge. But if you change your management, it will last. That's been my experience. But again, I'm not a
Maybe you take the sides and scoop it into buckets and then,
Sorry. So, in my particular context, we do a lot of livestock on perennial pastures. We do a lot of managed grazing. If you're cutting and taking it away, like Jimmy said in the last meeting, you got to leave something. You got to keep that soil covered. If that soil is bare any time of the year, if soil gets to 100, so if the sun's out and it's bare, the soil's bare, it gets up to 130 degrees, your biology is going dormant or dying. So it would last, but it will be determined upon your management. And either integrating livestock or not, do you have livestock? Do you guys do livestock at all? No. There's occasionally you could have partners that do use livestock. Oh yeah, everybody wants to graze your land, I bet. That's right. You got to find a manager who cares and who's really committed to it, and that usually means somebody showing up every day and moving those animals. And there's not a lot of those in Utah right now, but it seems to be changing, which is really great. 15 minutes, great. So this is just kind of a quick graph of what it looks like to be doing thermophilic compost. Thermophilic compost means getting your compost up to about 165 degrees for 24 hours and then turning it. Then you do that twice. You get all the material that's been on the outside that wasn't 165 degrees, put it inside. What that does is it burns out weed seeds, and it also eliminates pathogenic bacteria. And if it starts smelling bad, typically what's happening is your nitrogen, your phosphorus, potassium is starting to be off-gassed into the atmosphere. So you want to avoid that. You want to keep it aerobic. Aerobic is the key for keeping soils functioning, the soil that you want. And, yeah, go ahead.
It says keeping the pile 50% moisture.
Yes, sir.
How do you measure that?
So the way to measure that is you find several different spots in the compost, grab a handful, start squeezing. If a drop or two comes out, you're at 50%. Yeah, so that would be, yeah, you're 50. If you have like 7 or 8 drops, that's too much. Does that make sense? So if you squeeze a handful and 1 drop comes out, you're at 50%. This is the recipe I use, very simple. So high carbon, 60% would be wood chips. Wood chips, straw, leaves, anything that has a high amount of structure in it. Nitrogen, which would be green material. That high carbon by food, so that's why we put so much of that in there. And then nitrogen would be bacterial food, which would be, hay, not alfalfa. Alfalfa would be considered high nitrogen. But grass, hay, garden waste, stuff like that, scraps. And then high nitrogen, that would be party food. That's to get that thing up to temperature. That's for everybody to have a good time, get the party started. And that would be, chicken manure, cattle manure, horse manure. I would recommend manures that you haven't warmed your animal in. That will be a little bit challenging for the populations of organisms to get a little bit high. Also, alfalfa is a great one. Extraordinary, actually. I like alfalfa the most. It's the most consistent. And then you turn that twice. You get the big thermometer. You stick that in there. It gets up to 165, 24 hours. Turn it twice, and then usually let that thing mature, and the temperature should go down. It takes about 2 to 3 weeks. There are some inoculums that you can purchase that have all the protozoa and the nematodes and the fungi that you need, but there's usually enormous amounts of nutrients in there. Of course, yeah.
Also with the compost or manure, I don't know if that's to look out to also like the cows that have been eating the pesticides. You don't want to
Absolutely.
be careful with that.
Yes, you absolutely want to have you want to source high quality stuff. Sometimes cattle are not on the best feed. They will be high in salts, and you want to be watching out for that. So how do you implement this in different systems? So in a market garden or a garden situation, there's a couple of different ways to do this. This is one of our gardens that we have. In my opinion, the way to go no-till is to go through that layering process. Either you don't need a bed. We made beds just because it was convenient for us. Put down something that's going to start blocking out the weeds. Whether that's cardboard or newspaper or some kind of paper product, that's going to be fungal food. That will disappear really, really quickly. And then add your browns, so even more carbon. And then greens, vegetable scraps, things like that. For me, I'd try to put in either, if you can make compost, put that in. If not, even the biosolids you can get from municipalities is not a bad way to start. I don't love that, but incrementalism to perfection in that one, as my business partner James would say. So that's kind of what we did here. Here's a larger example of that. You don't necessarily have to till. Every so often you may need to start off with a market garden just to kind of set everything back in succession, because you're not trying to grow perennial grassland. You want to put that succession back into a little bit more. So you can see here that they've layered in straw mulch over the top of everything. And then as time goes on, that's going to break down and become more aggregated. The cardboard itself, you can do another layer of everything. And if the more you keep adding, the less weeds you have. It's not necessarily a bad thing to have a weed, just if you can get it out of there before it starts to seed out. Row crops. There's a lot of different ways to do row crops. This right here, I don't know if anybody's seen a picture of it, but that's a roller crimper. That's a good way to start managing cover crops if you don't have cattle. What that does is it knocks it down, and then behind the tractor they have there, that's a John Deere no-till drill, and they also have some inoculum in there as well. that you can coat seeds with that has all of this in it. So when it gets on that seed germinates, all those organisms are ready to go and rock and roll. And you put that right into the mulch that you're knocking down, all in the same pass. And that big drum there with the chevrons on it, you can fill that with water depending on your weight need. And this is kind of what it looks like, especially with corn. This would be interseeding with corn. And it'd be great to graze that, but you can also terminate that either with another roller crimper, with whatever your particular operation is. But you just want to have that ground covered. If it's not covered, fungi, bacteria, protozoa, it doesn't matter. It's going to get baked out of existence. Here's another example with rye that they're seeding into. And then if you don't have any of this, I'm going to be real honest, the only way to really achieve that is with livestock. Protozoa, if you till, same with nematodes, they're not going to, I'm not sure what the science is, but to have those come back naturally without introduction of some kind of livestock, especially their saliva. I've examined the saliva of our cattle. They have a lot of amoeba and a lot of flagellates in it. And their saliva is absolutely pivotal to get those organisms back in if you're not going to use some kind of inoculum. The fungi and the bacteria will come back over time, for sure, because the spores are fairly small. But the other ones, I don't know if they will come back. Now, there's a lot of nuance in this livestock world. There's a lot of different ways to do it. There's, holistic plant grazing, mid grazing, adaptive multi-paddock grazing. It's all somewhat similar with its own little specialties. But you got to do livestock right if you're going to introduce them. And there's several different other breakout sessions that we're going to be talking about today. Three Springs Land Livestock's one of them, if you want to learn more about that. This was a farm, excuse my commentary on it. This is a BDA farm in Alabama. This is, hey guys, they do this. How many head do you have here? This is just 250. This is a 2,300 ranch. And animals and 48 pads. Oh, you fill up the whole dude. That's one of the. I love seeing large animals. That are there. Biodiversity is absolutely pivotal for all of this, and the biodiversity in your soil will result in being able to. That will result in being able to support more biodiversity upstairs as well. So these are the soil food web, the soil health principles, the 6 of them. These are all absolutely important, and they all have to do with the soil food web. And for a lot of people, you don't necessarily need to know all these functional classes, but it's good to know, in my opinion, because it gives you a deeper distinction and appreciation for what's going on underneath. There are some new, if you can get a protozoa infusion into your ground, though, I'm telling you, we've done that in our greenhouse, and it's a little bit different. Anyway, I have some appendices, I guess, that talk more about nutrients, but if anybody has any questions, I think we're almost out of time. This is my name. This is our laboratory and website. If you have further questions or you want to talk, feel free to call. I live and die by loving to talk about this stuff. So appreciate your time, and if anybody has any questions, I'd love to answer them. Great. Oh, yeah. Yeah, of course. Oh, the last one. Oh my, I'm going the wrong way. Sorry. It doesn't sound interesting. Sorry, what was your question?
Yeah, so you initially said you did shadow microscopy.
Yes, sir.
For nutrient cycling kind of consulting or whatever.
Yeah.
Just a straight morphological characterization, are you doing like percentages or things like that?
So we are measuring fungal bacterial biomass. So we do determine that for you. We do measurements of the fungal weight and the bacterial weight, but then it's also morphological characteristics of the actual organisms that are present in the soil. Yeah. And you get a count, and then we say how many micrograms per gram. Yeah, so you can actually.
You have your own lab, right?
Yes.
You analyze right there?
Yes, we do. Yeah. Yes, sir. Is that the slide you're looking for?
Yeah.
Perfect. All right. Perfect. Well, thank you for your time. Appreciate it. Perfect. Let's leave that. Yeah, no problem.
Sorry about spending those.
No, you're good. That's your media.
Yes, so I'm with the Salt Lake Review.
Yeah.
And would love to connect with you at some point, just to talk about your work.
Sure.
Maybe we'll see some of it in person.
Yeah.
That'd be great.
My microscope is out of the country right now with my father. He's
Okay.
out of the country, but it will be back by the end of this month. And if you like, we could do. You can come and see how we actually do the assessment.
Sure, that'd be great. What is your phone number just the best way to reach you?
Yes.
Okay.
Yeah, that's the easiest way to get it.
Okay,
Yeah.
sounds good. Thanks.
Yeah, no problem. Thank you.
Good job.
Yeah.
Yeah, I really know that.
Yeah.
It's kind of mind-blowing at points.
Yeah, there's a lot there. If you have interest, it's just for me, it just defines it and confirms it more.
All the different types of fungi and things they do, even those that was like, I was scribbling stuff down. That's so cool.
If you want to see something that really gets your mind blown, on YouTube, it's called Journey into the Microcosmos. It's amazing. Yeah, and it's their imagery is they use the same microscope I use, but they use a little different ways to color it. And it's Journey into the Microcosmos. Yeah, it's really cool. Yeah, no problem. Thanks for your questions.
You're welcome.
Hey, good.
Yeah, I just had a question for the actual like biomass, like that grams per like grams per gram. Is that how you do the actual biomass?
We have a calculation. So what we do is we take usually from 1 to 10 solutions of 1 milligram per 10 milliliter, sorry. And we take a drop out of that solution. So we would have, say it's vermicompost or something. So we take 1 gram of that, 1 milligram.